Welcome everyone. Today we'll be discussing Chapter 7 Memory Management. This presentation is brought to you by Group 9, Chong Kai Siang, TUJ, Hannah Farzana Binti Kahiro, and Lo Yong Han. Let's dive into the key concepts related to how operating systems manage memory efficiently. We begin by discussing the best fit memory allocation strategy. Best Fit chooses the block of memory that is closest in size to the process request. The goal is to minimize wasted space by selecting the smallest available hole that can fit the process. This method is known for reducing memory fragmentation to some extent, though it can lead to many small unusable gaps over time. This slide presents an initial layout of memory with both used U and whole H. Each block has a defined size, and the process sizes are displayed at the top. We have four processes, P1 equals to 66, P2 equals to 45, P3 equals to 9, and P4 equals to 61. The goal is to allocate these processes into available memory holes based on the best fit strategy. Here, the memory blocks are evaluated based on their size to determine the available holes. The four memory holes are labeled H1, H2, H3, and H4. The sizes of these holes is calculated as follows. The sizes of these holes is calculated as follows. H1 is 50, H2 is 60, H3 is 80, and H4 is 140. These values will help us decide where to allocate each process. Now we apply the best fit method to allocate P1 and P2. For P1, the hole of size 80, which is H3, is the best fit, leaving 14 units of unused space. Similarly, P2 is allocated to H1, which is 50 in size, leaving 5 units unused. The algorithm ensures that each process occupies the smallest hole possible without wasting significant memory. Next, we allocate P3, which is equal to 9. The best fit for this process is H3. This leaves 5 units of unused space after P3 is placed. Finally, we allocate P4, which equals to 61. The best hole for P4 is H4, which has 140 units available. After allocating P4, we are left with 79 units of unused space. As we can see, even though the algorithm tries to minimize space, there is still some unused memory left. This slide provides a visual representation of how the processes are placed within the memory holes. Each process is mapped to a specific block of memory, and we can clearly see the remaining unused space in each hole. This slide summarizes the total allocation process, showing the cumulative sizes and how the memory blocks are being used. We can see the addition of values ensuring all memory is correctly accounted for. To recap, this slide reinforces the allocation decisions made using best fit. The process sizes and the remaining memory gaps are displayed, giving us an overall picture of how efficiently the memory has been used. Now we move on to the worst fit memory allocation strategy. In this approach, the system chooses the largest available block of memory to allocate to a process. This method tries to ensure that large blocks are used first, leaving smaller blocks available for future processes. However, it can lead to more fragmentation over time. In this example, we begin allocating processes using the worst fit algorithm. P1, which is 66 units, is allocated to H4, the largest hole available, which is 140 units. This leaves 74 units of unused space. For P2, with the value of 45, the system selects H3, the second largest hole, which is 80 units. After allocating, 35 units remains in H3. Similarly, P3 with a value of 9 is placed in H3, leaving 65 units of unused space. Lastly, P4 with a value of 61 is placed into the largest available hole, which is H4, where 65 units of space were left after P1 and P3. This leaves 4 units of unused space. Although large blocks are used first, this method can leave behind smaller fragmented blocks. Here we see a visualization of how processes P1, P2, P3, and P4 were allocated using the worst fit algorithm. The layout shows the remaining space in each memory block, highlighting the differences in fragmentation compared to best fit. This slide provides a summary of the worst fit allocations. The cumulative process values are shown, helping us visualize how the processes filled the memory blocks and how much space is still left unused. Now we look at another example of the worst fit algorithm. Like before, we allocate processes to the largest available memory holes, ensuring large blocks are used first. This can leave many small fragmented blocks. These slides walk through the allocation of processes P1, P2, P3, P4, and P5 using worst fit. In each step, we select the largest hole available and allocate the process, then update the remaining space. This slide provides a visual representation of how the processes from case 2 are allocated in the worst fit scenario. It highlights the fragmentation that occurs when large blocks are used first. The slide summarizes the results of worst fit allocation for case 2, showing the remaining gaps in the memory and how space was utilized. It helps compare the effectiveness of worst fit versus best fit. In this slide, we revisit the best fit algorithm with a new set of processes and memory blocks. This case reinforces the steps involved in minimizing wasted memory by selecting the smallest available hole for each process. We walk through another example of best fit allocation using processes P1 with a value of 17, P2 with a value of 28, P3 with a value of 37, P4 with a value of 69, and P5 with a value of 18. The processes are allocated in the available memory blocks based on the same principle, selecting the smallest block that can fit the process. This slide visualizes the allocation of processes from the previous slide. It shows the memory layout after the processes have been allocated using the best fit algorithm. Now, we look at another example of the worst fit algorithm. Like before, we allocate processes to the largest available memory holes, ensuring large blocks are used first. This can leave behind many small fragmented blocks. These slides walk through the allocation of processes P1, P2, P3, P4, and P5 using worst fit. At each step, we select the largest hole available and allocate the process, then update the remaining space. This slide provides a visual representation of how processes from case 2 are allocated in the worst fit scenario. It highlights the fragmentation that occurs when large blocks are used first. This slide summarizes the result of worst fit allocation for case 2, showing the remaining gaps in the memory and how space was utilized. It helps compare the effectiveness of worst fit versus best fit. To conclude, we've seen how both best fit and worst fit memory allocation strategies operate. Best fit tends to minimize wasted space but can leave small, unusable gaps. Worst fit preserves smaller blocks for future processes but may lead to larger memory fragmentation. Both algorithms have their strengths and weaknesses depending on the system's needs. That is all from us, Group 9, discussing about Chapter 7, Memory Management. Thank you for your time and have a nice day.